All right, I'm gonna blow through the quick review here, since it's been 2 weeks. We talked about Rutherford and how that he discovered that radiation is basically made of 3 things: beta, gamma, alpha particles. And he did that by taking this lead box with radioactive material, run it through charged plates. Beta moved toward the positive, alpha toward the negative, gamma didn't move toward anything because it's just photons, it's light. We talked about the Thomson model of the atom, the plum pudding model, and how that Rutherford came out and did his gold foil experiment and basically disproved that. Rutherford had a couple of conclusions. One of them is what's most of an atom made out of? Space. And almost all the mass is where? In the nucleus. And when he shot these particles through that gold foil, some of them really got deflected. And when they really got deflected, that meant they were doing what, according to Rutherford? Hitting the nucleus. Most of them, though, did what? Went straight through, and that's where he came up with the empty space idea. All right, so the Bohr model is the one we're going to be working from mostly. And we look at these energy levels. And remember, the numbers in this diagram tell us how much energy an electron has when it's in that particular energy level. And the only way you can move from one energy level to another, the only way an electron can move from, say, 3 to 4 is to do what? Gain how much energy? The exact difference between those two levels. That's the only way you can move there. So one thing that we talked about calculating and worked some problems on is how do you calculate how much energy a photon has when it's given off by an atom. And this is the equation. You take the initial energy from that chart minus the final energy, again from that chart, divided by h, which is Planck's constant. And that's going to give you the frequency in hertz. One thing that we have to do, though, the numbers in this chart are in electron volts. So we have to convert them over to joules first. And there's our conversion. So let's work that problem. Let's rework this problem right here just to make sure we know what we're doing. The frequency and the wavelength of a photon emitted when an electron makes a transition in a hydrogen atom from 5 to 3. So let's go back to our chart. At 5, the level is negative 0.54. And at 3, negative 1.51. So at 5, negative 0.54. And at 3, negative, If you, yeah. We're just tell them to come over here. Yeah. All right, so again, to calculate the frequency, we're going to go the initial energy. We're starting in level 5. Minus the final energy, so it's minus a minus, so it's actually plus. And all that's divided by Planck's constant, which I've got written over there on the board. I'm just going to round it to 6.626. All right, so if we calculate that out, this comes up to be 0.97 electron volts over Planck's constant. But remember, we've got to convert those electron volts over to joules. So let's do that down here on the bottom real quick. And again, the conversion's written over there on the board. 1 electron volt is 1.6 times 10 to the minus 19 joules. So that comes up to be 1.552 times 10 to the minus 19 joules. So let's divide that out. And that gives us 2.34 times 10 to the 14th. What would the unit be on that? Here's what you got to think about. A joule, what's a joule equivalent to? A newton times a meter. And a newton is a kilogram times a meter over a second squared. That's what a newton is. A joule is a newton times a meter. And we're dividing all that by this. So if you look, meters squared are going to cancel with that. Kilograms cancel with that. One of these seconds cancels with that. So we're left with nothing over seconds. How can we read something over seconds? Per, so we can say per second, but it's hertz. So that's, again, our answer, 2.34 times 10 to the 14th hertz. We're calculating frequency, that's the unit that we should come out with, hertz. Now, the other part of the question said find the wavelength. Let me make a little space up here on the board. How are we going to find the wavelength? Yep, we're going to use C equals lambda times frequency. We're trying to find the wavelength, so wavelength equals C divided by frequency. C is the speed of light, divided by our frequency. So now if we divide that out, we come up with 1.28 times 10 to the minus 6, and that would be what unit? Meters, because this is per second. It's going to cancel that and that. Meters. Makes sense. What kind of light are we looking at there? Yeah, it's hard to tell from that diagram. We don't have enough.
Oh, thanks.
Yeah, we need a little more information. All right, let's look at a couple more of these questions real quick. I think we went over some of these last time. But number 2, how much energy is needed to ionize a hydrogen atom in the N equals 4 state? What's ionize mean? To make it not just go to a different state, to make it lose it altogether, to make it shoot it out, give off that electron. And it turns out that amount of energy is equal to the amount of energy that an electron has in that level. So it's in level 4. Those energy levels are listed as negative, so we need to say we need to add 0.85 electron volts. So it'd be positive 0.85 electron volts. If you put exactly that much in, that electron will be lost. What do we call it when you... Well, I'll come back to that later. Let me hold off on that for a minute.
So when you put that energy in, it'll go to energy level 3?
No, it'll just shoot out. It'll leave the atom. That's what ionize means. It'll leave it completely. All right, 3. Which electron transition will emit a photon with the greatest frequency? Now here's the deal. Let's just look at it. Let me write down my choices over here on the board so I can remember what they are. So we're looking at 1 to 4, 3 to 1, 1 to 3, 7 to 3, and 5 to 2. Let's go back to our chart. We're looking for which one will emit a photon with the greatest frequency. Well, it's going to have the greatest frequency if it has the greatest difference in what? The energy, electron volts. And if you look at them, first of all, those going from lower to higher, are they going to be giving off photons? If you go from a lower to a higher. No. So we can eliminate 1 to 4 and 1 to 3. From there, you ought to be able to just look at it and tell. 7 to 3. We don't even have 7 listed on this diagram. But what you can see when things go down to 1, and what happens? It gets really big, okay? When you go down to 1. So your answer is going to be 3 to 1. When you go down from some level down to 1, you start giving off like UV light, which is really high frequency stuff, right? All right, 4. An electron in the ground state of a hydrogen atom can absorb a photon with any of the following energies except. It's E. Remember, the way you calculate that is you just subtract these from each other, right? And you figure out the differences. So the difference between this one and this one, the difference between this one and this one, and so on. And you find the one that doesn't match. And in that case, I think it was probably. All right, let's skip 5 because it's just like the problem we did a second ago. 7, how many different photon frequencies can be emitted if an electron is in an excited state of n equals 4? Let's think about this for a minute. If we're in the 4th level, the electron could drop from 4 down to 3, right? It could drop from 4 down to 2. It could drop down from 4 down to 1. But what else could happen? It could go from 3 to 2. It could go from 3 to 1. It could go from 2 to 1, right? So let's count how many things we got there. I think we got 6, right? 6 different kinds of light, 6 different wavelengths of light can be given off. Make sense? All right, let's look at this one. A radioactive atom emits a gamma ray. What happens? If you're giving off gamma rays, what are you giving off? It's pretty much pure what? Pure energy, essentially, right? Not any particles, not giving off protons or electrons or neutrons, you're just giving off energy. So when you give off energy, which one of those is happening? A. And the atom actually becomes more what? No, the gamma rays aren't charged. It becomes more stable. Less what? Yeah, less, and then less radioactive. All right, let's look at 9. An electron makes a transition from a higher energy state to the ground state in a Bohr atom. As a result of the transition, which one of those is true? Just going from higher energy to lower energy. What's our answer? Yeah, BB, right? Because the electron is moving from far away from the nucleus to close to the nucleus, right? And when you get close to the nucleus, you start getting held on too tight. All right, what about this one? How about C? Right, most of the mass of an atom is in the nucleus. Remember that the mass of an electron is so small that when we figure out atomic mass, what happens? We don't even count it in the periodic table, right? Doesn't even count, it's so small. All right, now these are two I don't think we looked at the other day for sure. If the source of light from excited hydrogen gas is moving toward or away from an observer, what changes, if any, are observed in the emission spectral lines? Stars are moving away from us right now, right? Supposedly the universe is expanding. And what happens to the color of light we see from those stars if they're moving away?
They turn red.
The waves get, the frequency gets what? Less. And if the frequency is less, the wavelength has to get longer. So what color do they start looking more like? Reddish. So if it's moving away, the colors are going to start becoming more toward the red end of the rainbow. On the other hand, if it's moving towards you, the waves get crunched together, right? And what happens when the waves get crunched together? The frequency goes up, the wavelength goes down, and it becomes more and more bluish. If we were talking about sound instead of light, what would we call that? It's a Doppler effect, right? Same thing. Same idea as the Doppler effect. And then number 12, a hydrogen atom contains only one electron. Explain why the emission spectrum of excited hydrogen gas shows the presence of many different spectral lines. If you took some hydrogen, and you guys have seen those little light tubes that we have, you know what I'm talking about? Everybody seen those tubes? You have hydrogen gas in a tube and you electrify it. Now, when you just look at it with the naked eye, it looks a certain color. But if you put a prism in front of that and you looked at it, what are you going to see? You're going to see lots of bands, and that's the emission spectrum. Why are we getting more than one color? Exactly. There's not just one hydrogen atom in that tube, right? There's bunches of hydrogen atoms. Some of the electrons may be going from level 4 down to level 3. That's going to give you off a specific color. Some may be going from 5 down to 2. Some may be going 2 down to 1. You're getting a different color for every drop, and different drops are happening in different atoms. All right, let's move away from that stuff, and let's talk about some really basic chemistry stuff here for a minute. Who in here didn't have AP chemistry? Okay, so about half and half. You guys know, well, I know you all know already that the nucleus is where the protons and the electrons are at. We can call a proton or a neutron a nucleon because it's in the nucleus. See that word nucleon? It's a proton or a neutron. The atomic number in physics, for some reason they call it Z. I don't know why they call it Z. That's the symbol for the atomic number. And the atomic number always tells you what? Number of protons. It's all about protons. The mass number, for some reason in physics they call it 8. Don't really know why. I guess it's atomic mass maybe. And that number is what? Protons plus neutrons. We have these nuclear symbols, like these two. It's uranium 92. 92 protons. If we want to find the neutrons, what do? Subtract them. So go 235 minus 92. Carbon 14. 6 protons and how many neutrons? 8. Now, what's an isotope? Just a reminder. We have different atomic masses because they have different what? Different numbers of neutrons. So if we put a symbol up here for normal carbon, carbon 12, it would look like that, correct? What does that tend to cause differences in? I mean, it's still carbon, but what's different about it? Stability. Which one of those is more stable? 12. Neutrons, their job in an atom is to do what? They help to apply what kind of force? It's called the strong nuclear force, or sometimes just the strong force. too many neutrons is just as bad as what? Not enough. Atoms become unstable when they have the wrong ratio of protons to neutrons. Because it's unstable, what do we know about carbon-14? It's radioactive. And what does it do to get back to stability? It shoots out stuff, right? And what do we call that? Radioactive decay, right? It decays. Radioactive decay. And when it decays, what happens to it? It becomes something else, right? And what do we call that when one element decays to become a different element? Yep. Walker said transmutation. That's a word that you might not know that you need to know after today. When one element goes through radioactive decay and becomes a different element, transmutation. Probably won't get there today, but we're going to talk about the different kinds of radioactive decay later. I had a cool lab plan where we were going to take some actual radioactive materials and Geiger counters. And the science and motion people, they don't have the lab anymore because somebody stole the radioactive samples from them. So wow. We can't do it. All right, just a couple of other things that you probably heard before. Protons and neutrons are almost the same size, right? Here's the mass of a proton. Here's the mass of an electron, or a neutron rather. Sometimes we use the term an AMU, atomic mass unit. And we can define an atomic mass unit several different ways. But essentially it's the mass of one what? What's an atomic mass unit supposed to be the mass of? A proton or a neutron. Look at the difference in them. We're talking about in the thousandths place after we multiply by -27. So we're talking very, very small differences. Officially, an AMU is this much. The AMU was, that unit was made up based on carbon, right? That's kind of what the whole system is based on, the carbon atom. So officially an AMU is 1/12 the mass of the carbon atom, carbon-12 atom. We just mentioned a minute ago the strong nuclear force and how it's the force that helps to hold the atom together, because what do protons want to do to each other? They want to push away, they want to repel. And the neutrons are in there to glue them together. That force, very, 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 very strong, but it only acts over tiny, tiny distances. Which force in nature is not the weakest force, but it can act over the longest distances?
Gravity.
Gravity. This is much stronger than gravity, but it will only act over tiny, tiny areas. All right, this diagram, what's it trying to show us? What's the blue line? What does the blue line represent? Yeah, well, the blue line is a prediction that maybe we ought to have the same number of protons as we do neutrons. That's what the blue line is showing us, if they were equal. And to begin with the small atoms, they are essentially equal, right? But then when we get up to the bigger atoms, the red line is showing us what actually is the best ratio for stability. As atoms get bigger, they need more and more and more what? Neutrons to be stable. That's what it's trying to show us. More and more glue to hold them together. Now this slide has a lot of writing on it. I usually try to avoid that, but this is stuff you may or may not have heard of before. Binding energy. If you're going to define binding energy, it's kind of what it sounds like it would be. It's the energy involved in what? Holding that nucleus together, binding it together. That's what it sounds like. What did Einstein tell us about energy and mass? Yeah, they're different versions of the same thing. That energy, that mass can be converted into energy, right? This is an example of when that happens. If you took the masses of all the protons and all the neutrons, the nucleons in an atom, and you added them up, and you compared that to the actual mass of that atom, guess what you find? They're really close, but the actual mass is actually a little bit less than what you think you ought to get when you add all the pieces together. Because some of that mass, when you put the atom together, does what? Gets converted into energy, right? Binding energy. The difference in the actual predicted mass and the mass that you really have, that's called the mass defect. So the difference in when you add up all the masses of the nucleons and the real mass, that's the mass defect. And that's always proportional to this binding energy, the mass defect. 1 AMU of missing mass, of mass defect, is equivalent to that many electron volts of energy. 931.5 million electron volts. So we might write that as a mega electron volt. Where do you think you're going? Wow. There's no other obligation besides physics. Slide. Sometimes you might want to look at the binding energy per nucleon. So if you calculated the binding energy of an atom, divide it by the number of protons and the number of neutrons, divide it by the mass number, and that'll give you the binding energy per nucleon. It turns out that the greater that energy, the greater the average binding energy, the more stable a nucleus tends to be. The greater the average binding energy, the more stable the nucleus tends to be. But what that ends up causing atoms to do, some atoms will naturally fuse together. So why are they fusing together? To get to more stable. Some atoms naturally split apart so that they can get to what? More stable. So fusion together, fission apart. And let me show you a diagram. This is trying to show you that the greatest binding energy is somewhere in that area, all right? That's where atoms want to be. So if you're a small atom, you're going to fuse with bigger ones to try to get to that area. If you're a big atom, you're going to split to try to get back to that area. So that's why this is called fission. These are going to split to try to move back to here. And this over here is labeled fusion because these are going to try to go together to get up to there. Yeah. No. Got to be at high temperatures essentially, right? Still got to be really, really hot for that to happen. Really, really hot.
They're working on it.
So, how does it become binding together? Just how they get like that binding energy.
Well, it's that whole mass gets converted into energy thing. It's the whole E equals MC squared thing. And that's, I know that causes headaches, but you just kind of got to take my word for it on that. I can't show you that happening.
Yeah. Do you know though?
Well, I mean, the mass is converted into energy. It disappears. That's why when you add up the masses of all the protons and all the neutrons in an atom, and then you weigh the atom, they're not the same. Some of the energy disappears. Oh, that's off. Hello. Hey. Jared Nelson. I didn't see him yesterday because of the ACT. He's in my. Wait a minute. Yeah, I did. Yeah, I did. He came in there first thing. No, he wasn't in there yesterday. No. Yeah, no, he wasn't in my room yesterday. He might have showed up. Yeah, he might have showed up and then disappeared. Okay. Thanks for watching.
Maybe you could plan to go to Texas to the super collider.
That would be cool. That would be cool. All right, real quick. We already talked about radioactive decay. When an atom loses particles or energy to get to a more what? stable place. We talked about transmutation. And that's again when a process, when an atom goes through radioactive decay and comes out what? As a different atom, as a different element altogether. Now, when we're talking about all this radioactive decay business, there's some symbols that you need to be familiar with. And this didn't turn out as good as I'd hoped it would on the screen. But these are some symbols you need to know, and you may or may not already know them. A neutron is going to be important in a lot of our nuclear equations. That 0 there means what? No protons. So that's like the atomic number and then mass number. So 0 protons, 1 neutron, and just an N. A proton we may write either way. There's 2 ways you might see it. Because a proton is essentially just like the nucleus of a hydrogen atom. So that's why we write it this way. 1, 1. That means 1 proton and 1 minus 1 neutron. So 0 neutrons. You might write it with the H, you might see it with the P. Either way, it's a proton. An electron. 0 mass number, which means no protons or neutrons, correct? And minus 1 is just telling us that it's a single electron. It's a charged, negatively charged particle. Sometimes you'll see E here. What else might you see there, depending on what that electron is doing? You might see a beta. And we'll talk about beta particles a little bit later. Beta particles are essentially electrons, high speed, high energy electrons. The alpha particle stuff. An alpha particle is a radioactive particle, right? Something that's emitted from a radioactive atom. It's essentially the nucleus of a helium atom. So it's helium minus what? The electrons. So it's 2 protons and what? 2 neutrons, 4 minus 2. So you might see it written as helium. That's an alpha symbol. It sort of looks like. That's the way you'll see me write it. Again, we talked about beta particles. They're high-speed electrons, so you might see 0 minus 1 E or 0 minus 1 beta. And then a positron, which you guys most of you probably never heard of before. A positron is sort of like a positively charged what? Electron. It's really tiny. Way smaller than what? Way smaller than a proton, but still positively charged. Yeah.
So, for the electron,
Mm-hmm.
for the neutrons, would it just be
For the electron? Well, that 0 means that number is the number of protons plus the number of neutrons, right? That's what that top number is. So that's saying there's no protons or no neutrons. It's just an electron. Yeah.
I remember hearing something about the positron being related to dark matter, or dark energy.
Yeah,
The space station detected it.
There-
and it's-
there's all kinds of theories there.
There's supposed to be a reverse, the beta particle, alpha particle, and the positron is opposite to that.
Right. We're going to avoid most of that discussion because we're still not sure. We will mention neutrinos and a couple of things along the way. They're still fairly theoretical. We're going to keep the radiation stuff pretty basic.
Wait, what were they? Dr. B invented that statement? We would know already.
There you go. That's it. That's it.
Well, while we're on particles, what particles do they use in the hadron collider? I keep hearing about using this hadron collider.
Yeah, we'll get into a little bit of that, but not in this unit. That'll be a little bit later on. So hold that thought. 'Cause I don't want to confuse everybody. That's that cause your headache kind of thing. Let's talk about alpha decay and maybe beta decay today, and then we'll be done for today. Alpha decay is a specific type of radioactive decay. You guys talk about this in APQM? Talk about radiation at all? All right. Here we have radium. Radium has 88 protons and whatever 226 minus 88 neutrons is.
Water.
Okay, there we go. When it decays, it tends to go through alpha decay, which means it shoots out one of these alpha particles. This is called the nuclear equation. And all these numbers have to add up for it to balance. It's sort of like balancing an equation. If this starts out at 226, the numbers over here have to add up to be 226. If this starts out at 88, the numbers over here have to add up to be 88. So when this thing shoots out an alpha particle, well, we got to go 88 minus 2, 86. And we've got to go 226 minus 4, 222. So what's left of radium after alpha decay is, what is that? Radon, right? Radon gas. This is kind of dangerous because why? If you got a lot of radium under your house, which you may, because there's radium in this area. There's a lot of radium under your house. Radium's a solid. This thing starts giving off alpha particles and becomes a radioactive gas, which can seep up through the ground into your house, and you can breathe it. And what does this do once it's inside you? It starts giving off beta particles and alpha particles in your lungs, and is one of the leading causes of what? Lung cancer in the world. And it's seeping up through the ground.
Is this a large supply here? Or is
It's
it like,
fairly common here, yes.
oh, right there.
That's why every so often in the school, you'll see them hang these little things from the ceiling. They look like little bird houses almost. And what those things are doing is they're testing for this. Now what would you do if you tested your house for radon and you found it?
Get out there.
Yeah.
Leave.
What would they do underneath your house?
Take it out.
They would put down some kind of barrier under your house. Maybe pour concrete if you're not on a slab. Maybe put down some kind of thick sheeting, and then also probably put fans underneath your house to blow it out so it didn't seep up through your house. There's ways around it being a huge problem. It's probably overblown in terms of the danger, like everything is.
So if you have concrete underneath,
If you got concrete underneath your house, this is probably not an issue. If you're on the slab, you probably don't have to worry about it. But if you got a crawl space, maybe you do.
oh, good. Why do you have to tell me?
Yeah.
Just don't say.
Here's uranium. Uranium is also naturally found in the ground, right? There are people who prospect for uranium. That's their job. They go out and look for it. One of the things that uranium do through radioactive decay is it'll give off alpha particles and become, what's TH? Thorium. There's actually a guy that you guys know Mr. Bennett, the sub here? Sometimes he subs here, Mr. Bennett. He actually used to be like a military person. I think he's a contractor now sometimes. They're actually talking about building nuclear reactors using thorium. Still got a lot of energy. A little bit more stable than uranium. All right, that's alpha decay. Last thing I'll show you, this is beta decay. Maybe the most famous example of beta decay is that top equation. That's what carbon-14 does to become stable. Where does that beta particle come from? Yeah, because notice your mass number doesn't change, but the atomic number goes up one. Essentially what happens is that a neutron splits. It splits into a proton and what? An electron. And there's a little bit more to it than that, but essentially, a proton and an electron. There's also some neutrinos and all that kind of stuff involved. We don't want to worry about that right now. Essentially though, a neutron splits into a proton and an electron. The electron gets shot out. That's what we call a beta particle. Shot out at a very high speed. The proton stays in the nucleus. The number of protons changed, so what had to change? If you change the protons, what did you change? Change what it is, right? It's something else. So carbon-14 eventually becomes nitrogen. Good old stable, this is a normal stable isotope of nitrogen, right? And this is the basis for why what works. That must have been a hyperlinked picture. That's the basis though for why what process works. Wow, silence. Carbon-14 dating, right?
Yes. Is that an exact science or are they?
No, it's not it's an estimation. But when you die, let's put it this way. After you die, Do you become more radioactive or less radioactive?
Neither.
Less.
Because you're not taking the radioactive stuff anymore.
Right. You become, hopefully, it'd be weird if you were, right? When you're dead, you're becoming less and less radioactive. And that's what carbon-14 science is based on. It's an estimate, but hopefully fairly accurate. Yeah.
Things that's not very good way today. They ever capture the electron themselves.
They capture it back. I wouldn't think so, but I can't tell you definitively. I'm not gonna answer that for sure.
So the Earth probably is about 6 billion years old.
Well, that's not based on carbon-14 dating.
Oh.
Carbon-14 dating is only accurate back a few